Good evening, Ramakant. Are you able to hear me? Ramakant, are you able to hear me?
Sorry, ma'am?
Are you able to hear me?
Yes, ma'am.
Okay, my camera is not working today.
That's okay, ma'am. So, no notes today or PPT will be there, right?
No, I will teach you.
You'll be sharing the slides, right?
Yes, yes.
Yeah, that's fine, ma'am.
So, are you able to see my screen?
Yes, ma'am.
Okay. So, in the last class, we studied about the yield point phenomena, strain edging, and dynamic strain edging, and a little bit about the precipitation hardening. So we will discuss in the detail in the precipitation hardening in detail. So in the last class, we the means precipitate which is given an intro to the precipitation hardening means the precipitation hardening it happens only when the solubility of the alloying element decreases with when we decrease means uh, solutionize or then the cool the material at room temperature. So what happened at room temperature if we left it for some days? So the solute atoms will precipitate out from the supersaturated solutions and form a precipitate of different morphology and sizes. So will so the first step in the precipitation hardening is the isothermal heating. For a certain period. And then the next step is the room temperature aging. Yeah, so the second step should be cooling, and the third step is aging. So aging can be done at room temperature or some elevated temperature. So the means the room temperature aging is known as natural aging. And the some elevated temperature aging is known as artificial aging. So the isotherm due to the isothermal heating for the of the alloy, the supersaturated solid solution is obtained. It is written as tetraisomere alloy. So if we have given some material of aluminium alloy, which is precipitation hardenable, so how can we designate is it natural aged or artificial aged? So there is designation with this, means the aging according to the different types of aging. So that is known as the alloy temper designation. So this is temper name and the condition. So as we know that the annealed sample is written as the A, sorry, O. So for temper also we have designation T. So first we will discuss about this, means the simple designation. F means the as fabricated. Then O is for annealed. W is represents the solution heat treated. And T is the temper. So the T can is further classified into uh, different conditions, like T1 is given as quenching from an elevated temperature. Shaping temperature shaping process plus natural aged, means the sample is quenched from a shaping elevated shaping process, then it was natural aged. Then the T2 represents means the same state, quenching from high temperature shaping process plus cold work plus natural aging. Then T3 represents the same, means quenching from high temperature shaping process uh, to artificial aging, means the it can also be written as double A. Then T4 is given as solution treated plus natural aged. Then, sorry, this previous was the T5. T3 will be solution treated plus cold work plus the natural aging. Then T6 will be is T5 is this means quenching from high temperature shaping process plus artificial aging. And then T6 will be solution heat treated plus solution heat treated plus artificial aged. Then T7 will be so the artificial aging is up to peak hardness. We'll further study that what is peak hardness or over hardness means over aging. So the T7 is solution heat treated plus stabilization. Stabilization is known as the overaging. Then T8 will be solution heat treated plus cool work plus artificial aged. And T9 will be solution heat treated plus first artificial aging, then cold working. And T10 will is the this quenching from high temperature shipping process plus the cold working, then artificial aging. Then some more temper designation are there. Means T651. This is stress relieving given by stretching to remove compressive stresses. And the T652 is given as stress relieving by compression to remove tensile stress, tensile residual stresses. So the 5-1 represents the stress relieving by stretching to remove compressive stress, and T652 is the uh, stress relieving by compression to remove the tensile residual stresses. So means what is the reason behind the compressive and tensile residual stress? Means during the fabrication process, either it is casting process the forming process or any additive manufacturing in which the high cooling rate leads to the uh, therm- generation of the residual stresses in the solidified component. So for that, and the what is the effect of the residual stress remaining in the sample? So the compressive stress means it decreases the structural integrity of the component. Means if we apply any pressure, so it will easily break. And for the tensile residual stress also, so if the tensile residual stress is present in the material, so that will decrease the yield strength of the material. So that's why we have to apply the stress relieving temperature to remove these residual stresses. Then, so how these tempers affect the means it increases the strength of the material while stabilizing the microstructure. So the if we do the solution heat treatment plus quenching, that will provide the supersaturated solid solution. Then after, with aging, supersaturated means the copper or any alloying element which are heat treatable in alloy, so that concentration is maximum. So the with time, the excess solute will precipitate out from the solid solution. With time and temperature and time. So there is a very important role of the temperature and time. Temperature and time on the this uh, precipitation hardening behavior of these alloys. So the temperature and time represents the kinetics of the process. So what is the kinetics? Means the diffusion of these solute atoms will differ, and with time also means they have time to rearrange in the solid solution. So that will also affect the uh, morphology of the precipitates forming during the aging process. So the lower or higher temperature uh, defines the determines the size of precipitates. Means if the temperature is low, so the size of precipitates will be very fine, and if the high temperature is applied during aging, so the precipitates will grow to a larger size. So generally the temperature given is 120 degrees Celsius. So based on this temperature and time, there are two types of graph. One is the equilibrium phase diagram, in which the phases are evaluates, and the temperature time transformation means TTT diagram. So first we will draw the uh, phase diagram for the solutionizing treatment. So this is the means aluminum temperature 660 degrees Celsius. So if we take this composition and heat it to a complete solutionizing temperature Ts, so at the temperature at which it is intersecting the solidus line, this is given as Tn, means Tn for the nucleation of solid. Then at the lower temperature. This is the supersaturated solution temperature. Means the cooling remains the solute in the solute solution of the aluminium and copper. So this is the temperature and this is composition. So what is the cooling rate effect? So if we draw the TTT diagram, this is the solvent means complete solid solution temperature TS, and there are the formation of the start and finish graph curve of the alpha solid solution and the theta precipitate. So alpha plus theta will form during this cooling range. So if the cooling rate is low, means this, so the low cooling rate curve intersects the start and finish curve of the alpha plus theta. So this will the low cooling rate will lead to coarser precipitates. And if the cooling rate is high, this, so it will not touch the start and finish curve of this alpha plus theta formation, and it means it lead to high finer precipitates. This is high cooling rate lead to finer precipitates. So this is temperature versus time curve. So now we know the natural aging is done at room temperature and the artificial aging is done at high temperature. So what happens during the aging means the excess or solute atoms extract out from the supersaturated solid solution and form a cluster. So the cluster of atoms generate during the aging on a particular planes. Called as so these clusters are called as GP zones. Means why I'm calling the particular plane, because the favorability of the clustering of these atoms is most high on these planes. So what are these planes? Like 100 plane. In the solidification process, the 100 planes first starts, means the atoms will first cluster on these atoms in every metal. Then the other planes are grow, because the surface energy of this plane is favorable for cluster formation. That's why the particular planes is chosen for the cluster of formation. So means what is these TP zones? In this, the aluminium and copper atoms are arranged in a sequential manner. So the also the aluminium and copper have some atomic radius difference. So because of that atomic radius difference, there will be mismatch between the aluminium copper arrangement. So this mismatch create lattice strand in the clustering of these atoms. So this lattice strain will further hamper the dislocation motion. and as the dislocation motion is hindered, so that will lead to strengthening. So we will discuss about the artificial aging now. So in artificial aging, there is one graph, uh, hardness versus time versus time. So due to higher temperature, the hardness will vary according to this curve. Means this hardness increases, then so there will be two peaks. Means so the highest peak is called the peak hardness value. So the means precipitates forming during this time. So first the GP zones are formed, then these GP zones converts into theta double prime. Then at peak hardness, the theta double prime will change to theta prime, and as the theta prime after the theta prime precipitation, if time is given at that temperature, so that will coarsen these precipitates and lead to the theta formation. So the theta are the coarser means coarsest precipitates in the system. So that's why as the precipitates portion, the hardness will reduce. So if we talk about the sequence, first the supersaturated solution is formed. So due to aging, the GP1 zone are formed. Then after with time, the GP2 zones are formed. So these GP2 zones are known as the theta double prime. Then the theta double prime will further change to theta prime and theta. So the theta is the overaging condition. So what is the mechanism between the changing in hardness with time at the during artificial aging? So we will there are six types of strengthening mechanism that will determine the hardness of this supersaturated the alloy after the aging. So we just discussed that because of this aluminum copper atom, there will be mismatch that lead to formation of the lattice strain. So due to the lattice strain, yeah, one more thing is that there is a interface creating between the cluster. Means there the as the cluster of these atoms are formed, so the cluster and the normal solid solution will have some interface. So that interface also classified into three types of interface. Means first is the coherent interface. Second is the semi-coherent, so semi-incoherent. And third is the incoherent interfaces. So what is the difference between these three interfaces? In coherent interface, the complete atom spacing will match to each other. Means there is very less lattice strain between the cluster atoms and the solid solution atoms. In the semi-coherent interface, the that lattice mismatch will further increase to a level where means the lattice strain can be accommodated due to the dislocation formation. And in the incoherent interface, there will be complete mismatch of the lattice between the cluster and the solid solution. So that will uh, so the coherent interface is generally exist in the theta double prime and theta prime. So theta double prime and theta prime precipitate have the coherent interface, and the theta precipitate is form the incoherent interface between uh, the precipitate and the solid solution, aluminum solid solution. So that will affect the mechanical properties according to the interface. So the coherent interface will generate the strengthening known as the coherency strain. So due to this coherency strain in theta prime precipitate, the change in applied stress will be 6 capital G R by V 1 by 2 f raised to power half square root, and the epsilon is 3 by 2. So here G is the shear modulus. R is the precipitate size. B is Berger vector. F is the volume fraction of the precipitates. And epsilon is the coherency strain. Means the coherency strain is helpful in increasing the strength of the material. Then there are other types of strengthening mechanism related to the precipitation hardening is the stacking fault energy. Means how the stacking fault energy of precipitate and the matrix are different. Means by what is the reason behind the energy difference between the precipitate and the matrix is the that we talked in the previous classes that the stacking fault energy is given as the energy divided by distance between the stacking fault. So the spacing between the stacking faults generated in the precipitate or matrix will define the their energy. So if there is the local variation in stacking fault width, variation in stacking fault width. So due to this stacking fault width variation, the further strengthening will be given as gamma m minus gamma p divided b, that will further divided into rho k alpha ln of b bm by b p divided e. Then this will be f1 and the f power 2 by 3. So the small f is known as the volume fraction of the precipitates. The capital F1 is the complex function of the stacking bit. The stacking fault width and the precipitate size. F is the volume fraction. K alpha here is the product of force separating two partials and distance between them. Means it is K alpha is written as the force and the distance between the stacking fault. Sorry. This means the force which separates the two partials and the distance between them. Further, this gamma MP and gamma P are the stacking fault energies, and V is the Berger vector, C is some constant, E is the elastic modulus, and Vm and Vp are the volume fraction of matrix and precipitate. Then the next type of strengthening, determining the precipitation hardening is the order structure hardening. So what is the order structure hardening? Means there is some ordering in the aluminum in the GP zones. So if the precipitates have some ordering, so due to this ordering, when the deformation happens, that order structure will break at some point, that will create the antiphase boundary between the matrix and the uh, precipitate lattice. So that will form the antiphase boundary. So this antiphase boundary is hinder the motion of dislocation. So the increase in the strength due to this order structure hardening is given as 2 divided by pi e gamma APB divided b 2 by 3, sorry, 3 by 2. R is the 1 by 2 and F is square root of F. So here R is the particle radius, F is the volume fraction of the precipitates, gamma APB is the antiphase boundary energy, B is the Berger factor, and E is the modulus. The next effect on the precipitation hardening is the modulus effect. So means the local change in modulus or between the precipitate and matrix lead to these modulus hardening. So local modulus effect changes in precipitate. So energy due to this local modulus change, the energy of dislocation will change. So that will create the strengthening by delta G divided by 2 pi square, then 3 mode of delta G divided GV power 1 by 2, then this is multiplied by 0.8 minus 0.143 R by V, and that is multiplied by square root of R and square root of the volume fraction. R is the particle radius, and B here also the Berger vector, F is the volume fraction, and G is the shear modulus. Then there is two more hardening. One is the interfacial. Energy means the interfacial energy role comes in the small precipitate size. Means if the small precipitate is there and dislocation is going through it, so the small precipitate will shear out due to this dislocation. So it means the precipitate will cut out because of this dislocation. So the creation of this surface means step means there is an increase in surface area of the precipitate. Because of this increase in surface area, the surface energy also increase. And due to this increase in surface energy, we have to apply more stress for the deformation to continue. And one more thing is that the step creation is equal to the Berger vector of the dislocation. So the step size is generally equal to Berger vector on the dislocation. So the stress change can be given as 2 square root of sigma divided pi, then this gamma s and f by r. So gamma s is the surface energy created between particle and matrix. Then the final strengthening mechanism in the precipitation hardening is the lattice friction stress. So the lattice friction stress is the stress required to move dislocation through the lattice. Means during the motion of the dislocation, the lattice friction is also feel by this dislocation. So this will always present when there will be precipitate or no precipitate. Means the lattice friction will always be there. So that will change in stress given as 5.22 1 by 3 r square root of r, then square root of shear modulus b square and the sigma p minus sigma m. So here the sigma p is the precipitate friction stress. Means when the dislocation is moving in the precipitate, so the precipitate friction will be also there. And sigma m is the matrix friction stress. So these are the 6 types of strengthening mechanism in precipitation hardening. So this is only up to the theta prime precipitate where the coherency strain exists. If the theta prime changes to theta, so the coherency will be lost. And theta is known as the equilibrium phase. Means there will be no change in the morphology of the theta, only it will get coarsened. So if the theta prime is if the theta is present in the matrix, so let's consider this is the dislocation line and these are two theta precipitates. So it will passing through these precipitates and it will form a dislocation line will go on these precipitates. Further, it will form this type of structure. Then after some point, the dislocation loop is generated on the precipitate and the dislocation line will form like this. And after some point, it will straighten out. So the dislocation straighten out is because of the surface tension at these points. So that's why due to the surface tension, the dislocation will straighten out after some time. So this is the means the dislocation hindrance when the theta is present. So because of this loop formation, the means any further dislocation line come on this point. So because of this dislocation loop, that will feel some means force opposite to the dislocation motion. So that force also changes with the means the spacing between these two atoms. Means as the theta coarsen with the time, So due to coarsening, the separation of these precipitates will increase. So due to this increase in distance between the precipitates, the dislocation can easily go through it and will face no force during the motion, and that will reduce the hardness when the theta precipitate coarsen. So when there is a optimum distance between these two precipitates, so the stress required to bend a dislocation in this previous condition is given as tau equals to GB by 2R. R is G is the modulus, B is virtual vector, and R is the distance between precipitate. No, 2R is the complete distance. So we now up to this point we discussed that the supersaturated solid solution first form the GP zones 1 and then GP2 zones, which is known as the theta double prime. Then it will change to theta prime and it will change to theta with overaging. So according to the different heat treatable aluminum alloy, these steps will also differ. Means if we talk about first the aluminum copper system, which is 2H series. So the copper atom form the GP zones in it. So the means the theta precipitate, the composition of the theta precipitate is CuAl2. Means the final composition of the theta will be CuAl2. So how the precipitate grow in the aluminum copper supersaturated solution? First, the GP1 zones are formed. So these are just the cluster of copper atoms on 100 plane. Then the thickness of this GP zone is only few atomic distance. So these clusters are further surrounded by aluminum atoms. By aluminum atoms and vacancies. So because of this aluminum atoms and vacancy presence, the atomic atoms will rearrange and form a different means GP2 zones, and also with the in aging thickness of the GP1 zones increases. Aging increases lead to thickness increase, and reaches a constant size. So at room temperature, due to room temperature aging, the size is generally 3 to 7 nanometer. And if high temperature around 100 degrees Celsius is provided for aging, so that will increase the GP1 zone size 10 to 15 nanometer. So if we talk about the copper content in the aluminum copper system, so it does not affect the size of GP zone, but affect their number. Means if copper concentration is high, so the GP1 zone number also be high. Means the GP1 zones will form at several spaces in the solid solution. And if the copper concentration is low, so only at specific sites the GP1 zones will form. So if we talk the aluminium 4% copper alloy, so in this the number of GP zones found are 10 raised to power 14 to 10 raised to power 15 per millimeter cube. And spacing between those GP zones is the 2 to 4 nanometer at room temperature. Means because of this high copper percent, the number of GP zones are very high and the spacing between them is also very less. So next the GP2 zones or theta prime forms. So in this the shape of this are in the disk shape. Means the GP1 zones grow and form a disk shape which is larger than GP1. So the diameter of this disk is around 30 nanometer, where we see in the GP1 zone, the maximum increase is only up to 10 to 15. So the diameter of this theta double prime disk will be 30 nanometer. And the thickness also increases up to 10 atomic planes. And the means generally the 4 nanometer. So here the theta prime precipitate number will be less as compared to the GP1, because the several GP1 zones more cluster more and form the theta double prime. That's why the number of this theta double prime is less than GP1. And the theta double prime structure is the tetragonal, in which its lattice parameter is 4.05 angstrom and C is written as 0.77 nanometer. So that means the theta prime precipitate contains the alternate layers of aluminium copper. on 100 planes. Next, the theta prime precipitate will grow from the theta double prime. So this has the CuAl2 composition. So the theta double prime disk shape precipitate will change into theta prime, which has the shape of pleat. These are the pleat shaped. And size depends on aging temperature. Means if the aging temperature is high, then the size of the theta prime will be very high. And if the aging temperature is low, so the theta prime size also be very fine. So the it has the 10 to 600 nanometer in dia, and thickness is around 10 to 15 nanometer. And then next is the theta precipitate. So this is known as the equilibrium phase. Means there will be no change in the composition after this point. Equilibrium phase CuAl2. So this is also tetragonal, coarse, and incoherent. So this is for the aluminum copper system. If we talk about specific aluminum copper alloys like aluminum alloy 2024, so it has composition around aluminum 4.4 copper, 1.5 magnesium, then 0.8 manganese. So because the magnesium is also present in this alloy, so that will form the GP zones will form of the copper and magnesium atoms. Means both will extract out from the supersaturated solid solution. So copper and magnesium cluster forms in this condition. So this is written as the supersaturated solid solution changes to GP zones. Then this GP zone will transform into S prime, which is given as the Al2CuMg. Then this will change to S precipitate, which has the same fixed composition of Cual2Mg. So this here in this case, this is the equilibrium phase. So directly from the GP zones, the S prime form and the S will grow with the overaging. So this 2024 is generally used in the T8 temper condition. T8 is the solution treated plus cold worked plus artificial aged. The one more aluminum copper alloy is the 2124, which have the iron and silicon also. So the iron and silicon addition in the 2024 alloy will ensure high fracture toughness. So this is also used in T8 condition. So due to the T8 condition, means it is solution treated cold work plus artificial yeast. So due to cold working, the dislocation density increases. And as the dislocations and density increases and the grain boundaries are also present, so the these dislocation and grain boundaries both act as heterogeneous nucleation sites. Nucleation site for GP zone for precipitates to form. So the T8 condition of this aluminum copper alloy lead to a yield strength of 0. Means the 0.2% proof stress of this alloy it will be 415 ampere, which is very high. I mean, generally the aluminum have around 100 ampere yield, 0.2% proof stress. So and the aluminum copper which is heat treatable. So in the T8 condition, the proof stress is around 400 ampere. So this is used for aircraft. Then this is further, if the T3 temper is provided in the this alloy, so that will give the proof stress of 350 ampere, and due to the T4 temper, so the proof stress will be 290. So the maximum proof stress obtained is for the T8 condition. Then next alloy will be there, means the 6X series alloy, in which magnesium silicon are present as the alloying element. So in this 6X series alloy, the means the sequence of the precipitate formation is the first supersaturated solution is present that will form GP zones. Then the beta prime precipitate of Mg2Si. Then this beta prime will change into beta, which is equilibrium phase of Mg2Si. So in this aluminum magnesium silicon alloy, the GP zones are first spherical in size. Then elongate with these spherical GP zones, then further elongate with aging in 100 direction, and later become needle shape. Means the final equilibrium shape will be needle shape for beta. So the needle shape is also not beneficial for the uh, mechanical properties. So only up to the elongated or spherical shape, the that will increase the hardness. So if we talk about the coherency between the beta prime precipitate and the aluminum matrix, so the beta prime precipitate is the semi-coherent rod shape because they are elongated with length 1 micron, and the dia is the zero point 0.1 micron. Then the beta precipitate is the equilibrium phase Mg2Si, and it has the FCC lattice with parameter 0.639 nanometer, and these are the pleat shape. So the sequence in this is the first supersaturated solution, GP zone, then the beta prime and the beta. So the temperature for this aluminum magnesium silicon is around 170 to 200 degrees Celsius. And so the ratio, if we talk about this magnesium silicon, it is 1.73 is to 1. So if the silicon is present in a small concentration, so the small concentration of the silicon increases the strength, and as well as decreases the corrosion resistance at the same time. So the low concentration of silicon improves strength and decreases the corrosion resistance. So we have to be uh, careful with the silicon addition in the 6X series alloys. So if we talk about the 6061 alloy of this same series, means aluminium, 1 magnesium, the 0.6 silicon, then 0.525 chromium. So this alloy is used in the T6 condition and has the yield stress of 275 ampere. In aluminum copper system, we was able to achieve the 415 ampere yield strength. So this is the intermediate strength alloy. And the application of this is in the architecture application. Architecture is structural. Then second alloy of this series is the double A 6262. So the 6262 has the same composition as the 6061 with addition of lead and bismuth also present in very small amount. So the presence of this lead and bismuth increases the machinability. And the copper is also present in this copper and chromium, like we talk the aluminum, 1 magnesium, then 0.6 silicon, and then 0.28 copper, 0.6 bismuth, 0.6 lead, and some very small amount of chromium is also present. So the chromium present is the green. It acts as the green refiner in the alloy. So this the 6 to 6 to alloy is generally extrusion friend. Uh, it can be extruded easily, and it has also less quench sensitivity. Means if sensitivity is high, so the um, it cannot be quenched from higher temperature, because that will impart the means residual stresses in the material, but it has less sensitivity. So this can be directly quenched from the extrusion temperature. Quenching from T5 temper. T5 temper, we know it is the means the quenching from high temperature shaping process plus artificial aging. So in this alloy, we can easily quench it from the high temperature. Then the 6 to 6 alloy is also present in the T9 condition temper. So this is the solution treated plus artificial aged plus cold worked. So this has the yield strength of 380 ampere. Means here the yield strength increased from the this 6061 alloy. So the 6061 alloy, 6063 alloy are known to have the uh, good surface finish. And the the anodizing can also be applied for different color appearance. Next, heat treatable alloy are the 7x series alloy, aluminum zinc. So aluminum, zinc, and magnesium is also present in some amount of this alloy. So the zinc and magnesium ratio in the 7000 series alloy is the 5:2. And also it can vary to 7:1. So the 7:1 ratio is generally found in the commercial alloy. And we know that the this 7X series alloy is mostly useful in the aircraft application. So the sequence of the GP zone formation and precipitate in this is the supersaturated solid solution forms first the GP zones, then eta prime precipitate will first form, that will change to eta. So the eta is the equilibrium phase. So this has the MgZn2. So in this also the GP zone first are the zinc cluster in spherical form, and then the magnesium atoms will join. So the after the means spherical shape, the neta prime precipitate are the plate shape. With continued aging, and the dia of this plate further increase with aging. And the thickness of these plates will remain same, means will be no change in the thickness, only the diameter of plate uh, is increases with the aging, because then maybe that means these are forming on the 111 planes, so only the growth on the 111 plane is most favorable. That's why the plate formation is means the dia of the plates increasing, but the thickness is not increasing. So the 111 plane are the most favorable for the eta prime precipitate. So the eta prime is the plate shape at high temperature aging, and the eta precipitate is the equilibrium phase with hexagonal structure. So in the 7X series alloy, these are means highest strength alloy in aluminum series, high strength alloy, and the further strength can also be increases with addition of copper percent. Means if we increase the copper percent in the 7X series alloy, so that will also improve the strength of these alloys. Means the generally the 1% copper is generally used, means these are preferred. So up to 1% copper, it will go into the GP zone formation. No, the up to 1% copper is soluble in the solid solution. So if we choose the greater than 1% copper, so the after 1% solubility, the extra copper atom will extract out with the zinc and magnesium atoms to form the GP zones and further precipitates. So it has uh, the addition of the copper increases the solver's temperature. Solver's temperature we know means this is the phase diagram. So this is the liquidus and this is the solver's line. So as the solver's temperature increases, means at high temperature, the formation of precipitates will be favorable. Means within the high temperature, we can form the precipitates easily. So this also further increases. It has also good stress corrosion resistance. Good stress corrosion. The stress corrosion resistance condition is generally present when the load is applied and some corrosive environment is also present around the component. So that will means the corrosion is generally decreases the service life, and the with application of load is also uh, reduces its surface life. So means the combination of the corrosion and stress will means the will not hamper the service life of this 7000 series alloy up to higher means longer time. So the that's why its stress corrosion resistance is higher for this alloy system. So for this the 7000 series alloy, there is some requirement to form the GP zones. Means only the homogeneous for GP zone formation can increase the its mechanical properties and corrosion resistance. Properties. So the homogeneous GP zone formation can be obtained at 115 to 130 degrees Celsius aging temperature. So the aging for this 7x series alloy is given in two steps. First, the it means the GP zone formation is allowed at the lower temperature. GP zones are formed at the low temperature, means this is 115 to 130 degrees Celsius, and then to form the meta prime we have to increase the temperature. And also the cooling rate also uh, uh, determine the formation of these precipitates. Means if the cooling rate is low, so this low cooling rate will directly form the meta prime and nita precipitates, so that the morphology of these precipitate due to the slow cooling rate is not beneficial to improve the mechanical properties. So only we have to apply means high cooling rates. High cooling rate and the aging in 2 steps. First, the GP zone form at low temperature, and that GP zone um, further changes into the meta prime at higher temperature. So generally, the high temperature is around means first the aging at done at 120 degrees Celsius for 1 hour. That is followed by uh, aging at high temperature. The high temperature is around 160 to 175 because its solvus temperature is uh, high, so that will help in the formation of the precipitate at higher temperature. So this is for today's class. Anyone has any doubt, or we can go to questions? Can you hear me? Yeah. Do you have any doubt?
No, ma'am.
Okay, so then we will go to questions. So, can you see these questions?
Yes, ma'am.
Okay, so first question says like for precipitation, for precipitates to form in an alloy, the solute atom solubility means what should be? First option says these should have limited solubility in the parent metal at room temperature. It should be insoluble in the parent metal at elevated temperature. Should not change with temperature or should increase with increasing temperature.
Should increase the increasing temperature?
Yes, D option is correct. Second question is that means solid solubility we means first from the supersaturated solid solution na? So for that the solubility should increase with increasing temperature, then only we will be able to achieve the supersaturated solid solution state. Next question is increase in strength due to coherency strain of precipitate and matrix will be related to volume fraction as
Root of uh, volume fraction.
sorry.
Root of volume fraction. F power half.
No, this is the volume fraction or square root.
Yeah. F power half.
Okay. Then next question is what does T4 temper in aluminum alloys refer to?
Solution treatment plus natural aging.
Yes. Then next question is in which of the following case of quenching medium precipitates are much finer if the alloy is subjected to same solutionizing and aging temperature?
Water quenching.
Yes, because the water can quenching will allow the
Faster.
higher cooling rate. Next question is strength and hardness of aluminum alloy decreases during overaging heat treatment because of
Coarsening of phosphate.
yes. And one more option is correct. with worsening, the precipitate also get incoherent interface.
Okay. The formation of incoherent.
Yeah. So C and D option both are correct. The sixth question is when precipitates shear out by dislocation, then strengthening due to an increase in surface energy is
Directly proportional to volume fraction
yes. And
and proportional to particle matrix surface energy.
yes, means this is given as the gamma by uh, sorry, directly yeah, gamma and F.
F power half, I think.
Yes.
Both of them.
Next question is when the aluminum alloy aged beyond the peak aging time, then
Strength and hardness of alloy decreases, but ductility increases.
yes, and the
And
interparticle spacing also
it
increases.
decreases. Increases or decreases, man? Because the size will be increasing, right?
If the number of precipitates are higher, then the spacing will be less. And as the if the precipitates grow, so the spacing will increase
Okay.
because the number of the precipitate after
Will
cooling
reduce.
will reduce.
Okay. Okay.
Next question is when dislocation moves through the ordered precipitate, then strengthening will occur mainly due to the formation of
Anti-phase boundary.
yes. Next question is which of the following is the correct precipitation sequence for aluminum copper alloy when subjected to artificial aging?
Second one.
Yes. Next question is what does T652 temper in aluminum alloy refers to?
Fourth one.
Yes. So that's all for today's class. Monica, do you have any doubt?
No, ma'am.
Okay. So can we end this session?
Yes, ma'am. Thank you, ma'am.
Okay. Thank you.